Welcome. Welcome, one and all. So, in this lecture, I will discuss the concept of estimation. Okay. So, actually, this concept of estimation, this is actually very useful or important, and today in the today's data science. Okay. So, in estimation, there are a concept of population and a concept of sample. So, what is this population? Suppose there is a city. Okay. So, say this city, it may be any city, say Delhi. This city is Delhi. Actually, Delhi is it is a state now. Suppose actually there is a state. So let us take this state Delhi, New Delhi. So about this Delhi, I want to estimate the per day average data uses. Okay, the average data uses for per person. Okay, per person. Means on an average, a single person, how much data he is using, he or she is using. I repeat that on an average, okay, each citizen of Delhi, okay, on an average, each citizen of Delhi, how much data he is using. I want to estimate this thing. Okay, so obviously, even why one would be interested to estimate this thing. Example, say I am a mobile operator and I want to launch a new data packs in Delhi. Okay, discussing that. Suppose I am a mobile operator and I am going to launch data pack in Delhi. So for that, obviously, I need that what is the per day data uses, average data uses for each citizen of Delhi. Wait, please. So for that, it is not possible that I go to every citizen of Delhi. I go to every citizen of Delhi who is using data and record his data uses. I repeat, in order to estimate this thing, it is not possible that I go to every. For this purpose, it is not possible for me or for anyone that he goes to every citizen of Delhi and record his per day data uses. Okay, so obviously, what we will do now to estimate that we will take samples from different parts of Delhi. We will take samples from different parts of Delhi, and from the data uses of these samples, from the data uses of these samples, we will try to estimate the per day average data uses for whole Delhi. Okay, so here Delhi, what I will call Delhi, I will call it my population. Okay, so what is population? Here Delhi is my population. Okay, similarly, suppose I am owner of a big fashion accessory brand. I am a owner of very big accessory brand, and I want to estimate now per day or the average. I want to estimate that what is the average expenditure. What is the average expenditure by per person? Okay, per person, average expenditure per person on a particular fashion accessory, a particular fashion accessory. Okay, so I am the owner of this big brand fashion accessory, and I want to launch a new store or a series of new store in Delhi. I am a owner of a big fashion accessory, owner of a big brand of fashion accessory, and I want to launch a store or stores in Delhi. Okay, for a store for this fashion accessory. So obviously, for that, what I need that what is the average expenditure? Okay, average average expenditure of any citizen of Delhi, which he or she is spending on this particular fashion accessory. Again, for this, it is not possible that I go to every citizen of Delhi and record his per day expenditure, or his not per day, his average expenditure. Okay, average expenditure on this fashion accessory. So once again, we will have different samples. We will have these different samples from the different parts of Delhi, and from the average expenditure, or from the expenditure of these samples, we will try to estimate the average expenditure per person on a particular fashion, on this particular fashion accessory. So here, Delhi, actually, it can be Delhi, it can be New York, it can be any big set. Okay. So what is population? So population is the larger set. It is the larger set, okay, about which, I repeat, population, it is the larger set about which we want to estimate something. Okay, so population, it is the larger set about which we are going to estimate something. So here it can be Delhi, it can be Kanpur, New York, okay, it can be any larger set of persons or things. Okay, and obviously about this larger set of things or persons, we are estimating we are estimating something. Now this is population, and what is sample? We know what is sample. Okay. Now, usually, please mind, for population values, actually, you can see here capital XIs. These are capital XIs. Okay, X1, X2, Xn. What are these? These are our population values. These are our population values or population units. Okay, so X1, this X1, okay, you can see this is the first population unit, X2, the second population unit, X3, third population unit or population value. Actually, in the actually, whether this example or this example, what will be this capital X1? This capital X1, it will be the first citizen. Okay, the first, actually, what we do, the citizens of Delhi, we give them some ordering. The citizens of Delhi, we give them some order that one citizen is given the first, that he is the first citizen, second citizen, third citizen, and nth citizen. Okay, so this n number of citizens which are using the mobile data, okay, which are using the mobile data, or which are expanding on this particular fashion accessory. And obviously, this capital N, it is very large. This capital N is very large. Because if this capital N is small, we don't need the sampling. When we require this sampling, when this N means the number of population units, okay, it is very large. If the number of population units is even, why not even 1,000, up to 1,000 or up to 10,000? Then we can actually approach, we can reach to every citizen of Delhi who is using mobile data, or who is spending on this fashion accessory. So we can reach and record their data uses or expenditure, okay, expenditure on a fashion accessory. So obviously this N, it will be either in millions, billions, okay. So capital X size, they denote are our population units or population values. And the small x size, you can see small x size, they are called our sample units. Okay, so our sample units, sample observations, okay, or sample values. So now obviously here what will be x1? Actually, if I talk in more proper sense, in the case of first one, the first example of per day data uses, what will be capital Xi means capital X1, X2, X3. Actually, earlier I told you these are the citizen. Actually, if I talk in more correct sense, okay, that for the first example, this capital XI, it will be the data uses of the ith person in Delhi. This XI, capital XI, it will be the average data uses or data uses of the ith citizen of Delhi. Okay, and what will be these small XIs? These will be the data uses. Okay, of any ith sample. If I write here small XI, okay, so it will be the data uses of any ith sample person. Okay, the any ith sample person or person which is selected as a sample observation. Okay, so small x size they denote our sample observations, and capital X size they denote our population values. Okay, now uh, if you see here this expression and this expression, okay, both are means. You can see that both are sum of the values divided by number of the values. Both are sum of the values divided by number of values. But this is the mean of sample, okay, and this is the mean of population. Okay, so for mean of sample, the usual symbol is X bar, and for the mean of population, the usual symbol is mu. Okay, and this expression means this one and this, they are variances. If you know the basics of a variance, then both this one and this one, and uh, even these, uh, they are variances. But this expression, this or this, they are variances for sample, because here we are having sample observations and sample mean. And what are these? These are variances of population. Why? Because here we have population values and population mean. Okay. So for sample variance, usually we will use the letter small s here. Okay. And for the population variance, we will use the letter sigma square. So these are the usual symbols. Please mind that most of the time, not all the time, most of the time we will be using these symbols. So one must have the understanding, one must be used to these symbols, that X bar, usually it will be our sample mean, as small s square, it will be our sample variance, and mu, it will be population mean, and sigma square will be population variance. Okay. So these are the things. Okay, say in the this case of estimating the average expenditure by per person. Okay. Now here, what will be capital XI? What will be capital XI or capital X1? Okay. So that will be the expenditure by the first person of Delhi or whatever the population. Okay. It will be the expenditure by the first person who is who is spending on this accessory. And what will be X2? It will be the expenditure of the second person. Okay. Who is spending on this accessory. Okay. So now, yeah. So there, these results are there, and these are very important. Actually, these are the building blocks. These results, they are the building blocks of this whole chapter, okay, or estimation. First, this is expected value of xi, means ith sample observation. The expected value of, just wait, there is an issue. Yeah, sorry. Thank you. So expected value of ith sample value or ith sample observation, this is equal to population mean. Expected value of sample mean. The expected value of sample mean, this is also equal to population mean. Okay, and actually, if you know that if I define the expected value of any random variable x, the expected value of any random variable x, actually it gives you mean value or average value, mean value or average value of x. So here, expected value of sample mean. Expected value of sample means this is average of or mean of. Okay. So this is mean of sample mean. What is expected value of x bar? It is mean of sample means or average of sample means, which is equal to population mean. Variance, V stands for variance, variance of ith sample observation. Okay, this is population variance. And variance of sample mean, it is sigma square population variance divided by n sample size. This small n, this is what we call sample size. Expected value of sample variance, the expected value of sample variance, it is n minus 1 by n times population variance. And expected value of capital S square, where what is capital S square? Here it is given. Its expected value is sigma square. Okay. So one by one, I will derive all these results, but small s square, that is 1 by n summation xi minus x bar square. Okay. So this is sample variance. And in capital S square, this summation is same. You can see this summation is same. Instead of n, what we have? We have n. Oh, sorry. Instead of n minus 1, here it is n minus 1, we have n. Okay. So that's why n into s square, that will be n into s square. It is n minus 1 into capital S square. One can very well feel how this summation, this is n times s square. This summation, it is n times s square, and same summation, it is n minus 1 times capital S square. Okay, so this relation, it is very important relation because this we will use. So from here, s square means small s square upon n minus 1. This is equal to capital S square upon n. Okay, so whether you write like this or like this, so these are important. Now, expected value of xi means the ith sample observation. It is actually capital X1 into 1 by n plus capital X2 into 1 by n going on capital Xn into 1 by n. So this is the expected value of ith sample observation. Why? If you know that how we define the expected value of any discrete random variable. So for example, suppose my gx is the function of gx, say this is 2x square minus 3x, and x takes the value say 0, 1, 2. Okay, so here what is x? X is a discrete random variable. Why discrete? Because x is taking countable values. X is taking countable, means I can count these. This is the first value, second value, third value. So discrete random variable, if it takes countable values. So now what is expected value of this gx? So actually this is expected value 2x square minus 3x. So it is actually summation 2x square minus 3x into probability that x takes the value x. And this x, it is from 0 to 2. So expected value expected value of any function, expected value of any function, it is actually the values of the function into the probability, the corresponding probability. Okay, so actually here this one, this is what you called PMF, the probability mass function. okay, which is actually a probability distribution function. Okay, so this is now 2 into 0 square minus 3 into 0, and px is 0. Then 2 into 1 square minus 3 into 1 into, wait, uh, so here, uh, probability x is 1, and 2 into 2 square minus. So what are these? This one, this one, this one. These are the values of this function. This one, this one, this one. These are the values of this function at x0, at x1, x2, and multiplied by what? The corresponding probability. So here, this is the, so this one, it is the value of this function at x0 into what? Probability that x takes value 0. And what is this? The value of this function at x equal to 1 into the probability that x takes the value 1. Okay, and here this is the value of the function at x2 into the probability that x takes the value 2. Okay, so what is expectation of any function? It is a discrete function of a discrete random variable. It is the values of the function into corresponding probability and then summation over the entire range of the random variable. Now, this xi, what is this xi? This is our ith sample observation. Now, this ith sample observation, it can be my first population value, it can be my second population value, or it can be my nth population value. In other words, my first population value, it can be my ith sample observation. My second population value, even it can be my ith sample observation, or xnth, the last nth population value, it can be my ith sample observation. Ultimately, our sample observations, they are coming from population itself. Okay. So, for example, suppose once again, I have say capital X1, capital X2, capital X3 going on, say up to capital N, where N is in millions or billions. Now, if I am choosing my sample observation, Xi, so that one, it can be my, this capital X1, it can be X2. Okay. So, and so on. So, this Xi, it can take what values? This xi, small xi, it can be either capital X1, capital X2, capital Xn. So, what are these? The values taken by xi. Into what? What is this? This is the probability. Probability that xi takes any of these values. How? Because we are selecting single sample observation. We are choosing selecting single observation, ith observation, and we are selecting single ith sample observation out of total how many? Total n. So what's the probability of selecting one item out of total n? That is 1 by n. Okay. So here, this is the corresponding probability. So now, what is this expected value of small xi? This is x1 plus x2 going on xn divided by n. And what is this? It is population mean. Okay. Now, one thing here, our sampling is called simple random sampling. It is called simple random sampling. What is simple random sampling? If all these sample observations means small x1, x2, small case x1, x2, xn, if all these sample observations, they are independent of each other. Okay, first thing, and every sample observation, okay, it has same probability. Every sample observation or every you can say capital Xi population value, it has same probability for being there in our sample. Means x1, it will have the same probability that it can be in the sample. Even x2 can be the same, x2 will have the same probability that it can be in the sample. Okay, means we will not give preference to any population so that it can be in our sample. Okay, so now expected value of x bar. So or I can write like this. Wait, please. Yeah. So sample mean, it is nothing but x1 plus x2 plus, okay, whatever. Now this is this 1 by n. Actually, expectation is linear in nature. Okay, so this is a linearity property of E. Okay, expectation. And so this is expected value of x1, x2. Okay, now what is this value? Mu, and this mu, and this, even it is mu, because expected value of any ith sample observation, the expected value of any ith sample observation, it is mu. So here this I, xi, it can be 1, it can be 2, it can be n, means all these x1, x2, xn, their expected values, they will be mu. Okay. One thing here, that expectation is linear in nature. Actually, expectation behaves just like differentiation integration. Okay. For example, if you differentiate n functions, sum of n functions, they say d by dx of say c1 f1x plus c2 f2x. Okay. So this is actually c1 differentiation of first function plus c2 differentiation of second function, and it will go on like that. Okay, if it is up to nth function. So differentiation is also linear in nature, and even integration. Okay, means if I integrate this with respect to x, then that will be c1 into integration of f1 plus c2 into integration of f2. Okay, so just like uh, differentiation and integration, expectation is also linear in nature. Okay, so this is linearity property of expectation. So now it is 1 by n into n mu, that is nothing but mu now. Okay, so this is the second result. This is the first result, second result. Now, variance of xi. So now it is expected value of xi, sorry, yeah, xi minus x and whole square. Actually, variance of any random variable x, it is expected this thing. Okay. Actually, variance is also equal to, so variance of any random variable x, it is expected value of x minus expected value of x whole square. Also, it is equal to expected value of x square minus square of expected value of x. Variance of x, it is expected value of x square minus square of expected value of x. So even it can be proved that this expression is equal to this. So whenever possible, I will prove this also. Now, here, what is our random variable x? It is nothing but xi. Okay, so you can very well see that instead of this x, I have xi. So what is this thing? It is mu. And now what is this? X1 minus mu whole square into 1 by n plus, okay. Now, expected value of xi means expected value of some function. Okay. And now this is mu and square. They are constant. Please mind mu. It is mean. Mean is always constant, and a square is also constant. So mu takes the value mu. Okay. Constant 7 takes the value 7. Square takes the value square. Basically, this xi, either it can have value capital X1, capital X2, capital Xn. Means our sample observations, xi's, our sample observations, ultimately they are coming from population. Or my capital X1 means first population value, it can be my ith sample observation. Second population value, it can be my ith sample observation. Going on, the nth population value, it can be my ith sample observation. Okay, so now what is this 1 by n? The corresponding probability. What corresponding probability? That this xi, it takes the value capital X1 or capital X2. Okay, so on. Means that we are selecting ith one single observation. We are selecting one single observation out of total how many? N. Okay. And that probability is 1 by n. And okay, so this now, so this is nothing but our population variance. This proves our third result. Okay, wait, please. Now this. Now, uh, variance of this sample mean. So this is actually nothing but this expression, and this is now 1 by n square, then variance of x1 plus variance of x2, so on variance of xn. Why? Variance of a1 z1 plus a2 z2 and going on a n zn, means up to a n zn. This is a1 square variance of z1 plus a2 square into variance of z2 and an square variance of z and z or z, okay, whatever the pronunciation, okay, and plus 2 times ai, sorry, here it should be double summation with, so ai aj covariance between Zi, and Zj. Okay. And moreover, here I must be less than j and both are between 1 to n. So actually Z1, Z2, Zn, they are wait. So Z1, Z2, Zn, they are random variable, and a1 a2 an, they are arbitrary constants. So variance of this combination, linear combination of z1 z2 zn, it is a1 square variance of z2 plus a2 square going on, and this one. Now this result, even it can be proved. So once again, if time is there, I would love to prove this also. Now if these Z1, Z2, Zn, if these are independent, then this covariance term, it will be zero, because covariance, it is a measure of variance, it is a measure of dependency. In other words, that how two random variables are varying with respect to each other. Covariance. How two random variables, zi, zj, okay, how they are varying with respect to each other. That is measured by covariance. But since Z1, Z2, Zn, they are independent, so what will be covariance? It will be zero. Okay, means if the random variables are independent, then the covariance is zero. So now here, if you see, what is your Z1? Z1, instead of Z1, you have X1. Instead of Z2, you have X2, and so on. Now, what is A1? It is 1 by n. What is A2? It is 1 by n. And similarly, all the arbitrary constants are 1 by n. So, 1 by n square means A1 square, variance of this, plus 1 by n square into this, plus going on. Okay, means here all these a1 square, a2 square, an square, they are 1 by n square, and our sample observations x1, x2, xn, even they are also independent. I told you that our sample observations are independent because we are having simple random sampling. Okay, so now this is means variance of x1, it is sigma square. Variance of x2, even it is sigma square. Variance of xn, sigma square. Why? Because variance of xi, it is equal to sigma square. Okay. So here I can be 1, 2, whatever. Okay. So now, okay. So this proves variance of sample mean. This is population variance divided by sample size. Okay. Expected value of sample variance. This expression, it is also sample variance, and this expression, this is also sample variance. It can be proved that this expression is equal to this expression. Okay. So actually for all these proofs, I will try that if some another video is there. So I will upload that. So now, expected value of this expression. So it is 1 by n expected value of first term. Okay, this term minus expected value of this term. Once again, linearity of E. Now, here it is expected value of sum. Expected value of sum. And here it is sum of expectation values. Here, expected value of sum. Here, sum of expectation values. You can very well see that expectation and sum, they are interchanging their positions. Okay, how? Summation, oh sorry, expectation. So, okay, so expected value of this sum, I am talking about this. It is now this sum x1 square, x2 square up to xn square. And this is expected of x1 square plus x2 square going on. Once again, wait. Yeah, once again, the linearity of E. Now, so that's why this is now summation of expected value of xi square. Okay, so obviously summation is from I1 to small n. And please mind here there is one capital N which is the population size, and there is a small n which is the sample size. Okay, so now that's why this term is this. And now a very important formula that I already that we will use here. It is that if I go back, yeah, here. Okay, if I write, wait. Yes. So, uh, this one. So mark it, say this one is equation number 1. Variance of any random variable x, it is expected value of x square minus square of expectation x. Okay, just wait please. Yeah. So now expected value of x, yeah. So expected value of x square, it is variance of x plus square of expectation x. This term we can shift to this side. You can see this term, okay, it is here. So now this formula, that expected value of x square, where x is any random variable, it is variance of x plus square of expectation x. Even it is one more important formula that we will be using in this concept. Okay, so look here. Here, instead of this capital X, what I have? Small xi, ith sample observation. And here, instead of this x, what I have? X bar, sample mean. So, now, uh, yes, this thing. So, 1 by and variance of xi and this thing. Oh, wait. Yeah, yeah, this thing and scale. Means expected value of xi square, expected value of xi square. What is that? It is variance of xi, okay, plus square of expected xi, and obviously here bracket. And what is expected value of x bar square? Here, variance of x bar plus square of expected value of x bar. Means I have used, yeah. So expected value of sample variance. Okay, here from here. Okay. So 1 by n. Okay. Then summation of this. Okay. And then this term. So I think this is clear. Actually, I'm doing nothing. I am using this formula. Okay. One time for x size. Okay. And one time for x bar. Okay. You can see here. Now, 1 by n. Now this is, what is this thing? Sigma square. And what is this? It is mu and square. Okay. So what is sigma square? Population variance. Okay. And what is mu? Population mean. And now minus. Uh, okay. So variance of sample mean, it is sigma square by n plus expected value of sample mean, it is mu. Okay. So uh, I think it must be clear that here we are using this formula. One time for xi means this one time for this, and one time for expected value of x bar. Wait, please. Here, yes, x bar and square. Okay. So here, actually, uh, from equation 1. We may write from equation 1. Okay, here. So now, wait, 1, I1. This sigma square and mu square, they are constants. Okay. So population variance, and actually variance and mean, they are always constant. So you are adding a constant here. Summation means adding. You are adding a constant. How many times? N times. You are adding a constant n times. So that's why it is n times the constant. And remaining is as it is. And this cancels now. So even this mu squares cancels. And now 1 minus 1 by n sigma. Oh, wait. Okay. So actually 1 into sigma square. Okay, that is here, and minus 1 by n into sigma square, which is here. So, okay, this thing. And this proves our one more result, that expected value of sample variance is equal to n minus 1 by n times sigma square. So I have already discussed this formula. Okay, now taking expectation on both sides. Yes. So this expression is equal to this, and taking expectation on both sides. So actually, once again, here we are using the linearity of E. One can see, okay, n minus 1 and n, they are outside the expectation. And this term, it is here now, okay, means it is coming to this side. And what is this thing? N minus 1 by n into sigma square. Our previous result. And now you can see this will cancel out. Okay. And what is this now? Sigma square. So expected value of capital S square. The expected value of capital S square. It is equal to population variance. Okay. So here now we have proved all these results. Okay, so please mind these 5 or 6 results. Okay, they are actually important. So if you want to have a good grip, if you want to feel confident, anyone, me, you, anyone, if he wants the good grip, he expects the good grip on this concept of estimation, then he must be able to, first of all, he must be able to drive all these expressions, and he must be knowing the meaning, that how to read these expressions. Okay, so thank you for this. Just wait, let me see if I have to discuss. Okay, so thank you for this lecture, and now rest I will discuss in the next lecture. Thank you, everyone.